All right, let's jump right in. We have this idea that our brain is like a computer, hardwired and fixed. But the reality is so much cooler than that. Your brain's wiring is alive, it's dynamic, and it's constantly changing with every single thing you do and experience. So today, we're going to pull back the curtain and see exactly how that happens, right down at the nuts and bolts.
But first, let me ask you something. Think about your favorite memory. Or, hey, even just what you ate for breakfast this morning. Is that memory a thing? Is it a physical object that exists somewhere in your head?
Believe it or not, the answer is yes. They absolutely are. And this is where they live, in these tiny microscopic gaps between your brain cells. We call them synapses. The strength of these connections is literally where your memories, your skills, and even who you are is physically written into the fabric of your brain. And this incredible ability for the brain to physically change its own wiring, well, that's the secret sauce. That's how we learn, how we adapt, and how we remember anything at all. Neuroscientists have a great name for this: synaptic plasticity. Now, it sounds a bit technical, but the idea is actually super simple. The connections between your neurons aren't set in stone. They can get stronger or they can get weaker, and it all depends on how much they're used. This is the absolute bedrock of learning. So to really get how this works, we need to understand how neurons talk to each other. Imagine one neuron gives another one a little electrical nudge to try and get it to fire its own signal. In the biz, we call that nudge an excitatory postsynaptic potential. Yeah, it's a mouthful, so we just say EPSP. For the rest of this explainer, just think of that nudge as the volume of the conversation between neurons. Our whole story is about how the brain turns that volume up or down. So, let's start with turning the volume up. How does the brain take a connection, a pathway for a memory or a new skill, and make it stronger, louder, and way more efficient?
This process is called long-term potentiation, or LTP for short, and it's exactly what it sounds like. It's a long-lasting power-up for a synapse, making the communication between those two neurons way more effective. This is how a memory gets burned in, how it sticks.
And this chart shows LTP in action perfectly. Look at the before bar on the left. A normal signal comes in, you get a normal-sized nudge, a standard EPSP. But then, you hit that synapse with a rapid-fire burst of signals. Think of it like cramming for an exam. And now look at the afterbar. The exact same input signal now produces a huge response. The synapse is potentiated. The volume is cranked to 11.
Okay, so how in the world does that happen? What's the molecular switch? Well, it all comes down to a really special little protein, a key player in this whole story, called the NMDA receptor.
Scientists have this fantastic nickname for the NMDA receptor. They call it a molecular coincidence detector. And that's because it's really picky. It will only open up and do its job if two very specific things happen at the exact same time.
Let's walk through it. First, a ton of signals arrive one after another super fast. This gets the receiving neuron all fired up. Electrically speaking, it becomes depolarized. Now that strong electrical charge is just what's needed to pop a tiny magnesium ion out of the NMDA receptor's channel, kind of like a cork out of a bottle. With that channel now unblocked, a massive flood of calcium ions can rush into the cell. And that calcium flood is the master signal. It kicks off a chain reaction that tells the cell, hey, this connection is important, which leads to more listening posts, called AMPA receptors, being inserted into the synapse. The result? The connection is now way more sensitive.
Okay, so that's how we turn the volume up. But just as important, the brain needs a way to turn the volume down. It's got to have a way to weaken connections that aren't really useful anymore.
I mean, just think about it for a second. If every connection in your brain only ever got stronger, what would happen? It would be total chaos. Every synapse would be maxed out, just screaming at full volume. Your brain would be completely saturated, and you wouldn't be able to learn anything new.
And that's where the other side of the coin comes in. Long-term depression, or LTD. And no, it has nothing to do with feeling sad. This is a precise surgical weakening of a synapse's strength. It's the brain's essential tool for fine-tuning its circuits, for forgetting the unimportant stuff to make room for what actually matters.
And you can see the result right here. Instead of a rapid-fire burst like with LTP, LTD is triggered by a long, slow trickle of stimulation. Kind of a boring input. And after that, the same signal as before produces a much smaller nudge, a smaller EPSP. The synapse has been depressed. Its volume is turned way down. The mechanism here is just so elegant. It's basically the mirror image of LTP. So first you get these slow, low-frequency signals just trickling in. Because the stimulation is weak, the NMDA receptor only opens a tiny crack and just for a moment. This means instead of a flood, you just get a small, slow trickle of calcium into the cell. And that small, slow trickle is the key. It activates a completely different set of enzymes. And what do these enzymes do? They start pulling those AMPA receptors out of the synapse, making it less sensitive. The brain is effectively saying, you know what? This connection isn't that important. Let's quiet it down.
So a big, fast flood of calcium makes a connection stronger. A small, slow trickle makes it weaker. But it gets even more precise than that. Neuroscientists have found an even more elegant rule that governs this whole dance. It's not just about the rate of the signals, it's about their precise timing.
What it all boils down to is cause and effect. The brain is constantly trying to figure out if an input from one neuron actually helped cause the next neuron to fire. And it figures this out by measuring timing differences down to the millisecond, thousandths of a second.
And here it is, the golden rule. It's called spike timing-dependent plasticity, and it is beautifully simple. If the sending neuron fires just before the receiving neuron fires, the brain goes, aha, that first one caused the second one. This is a useful connection. And the result? LTP, the connection gets stronger. But if the receiving neuron happens to fire before the signal from the sending one arrives, the brain concludes it's just a coincidence. That connection is irrelevant. The result? LTD, the connection gets weaker. It all comes down to that classic saying, neurons that fire together, wire together.
Okay, so let's zoom out from all the molecules and receptors. What does this constant back and forth, this two-way street of strengthening and weakening actually mean for us? Well, it means pretty much everything. This constant, delicate dance between LTP and LTD is the physical process behind just about everything your brain does. It's how you learn to play the guitar, how you store the memory of a conversation, how your brain developed when you were a kid, and how you adapt to every new experience you have. So if there's one single thing to take away from all this, it's that you are not a static person. Every single book you read, every conversation you have, every skill you practice is physically, tangibly changing the structure of your brain, one synapse at a time. You are, quite literally, a work in progress. And that leaves us with one last big idea to chew on. If your brain is physically being reconfigured by everything you experience today, then who are you deciding to become tomorrow?